Hello chemists, and welcome to our lab on the determination of the water of hydration of alum. In this lab, we're going to do an experimental measurement of the water of hydration in a substance called alum. Hydration is the idea that water molecules actually get trapped in the formation of crystal structures, particularly of ionic compounds. So the water of hydration is the number of waters that have been trapped. For example, an Epsom salt that you might use in your bathtub, people always think it's just magnesium sulfate. It's actually magnesium sulfate dot, which means it's associated with 7 H2Os. So there's actually 7 water molecules trapped for every 1 magnesium sulfate in the crystal structure. What we're going to be doing in the lab today is we're going to be utilizing alum. Alum is KHSO4 in parentheses 2 dot XH2O. And that X is what you're going to be determining in the lab, which is the number of waters that get trapped every time that crystal forms. We're going to be doing this measurement both experimentally and theoretically. Experimentally means with the measurements you're using in the lab. So you're going to measure first your hydrated alum on the scale. And then we're going to heat it up on our hot plates until it dries out. And we'll know it's dried out or that the water has left because the mass will start to stabilize. We'll make several measurements after they cool to see that the mass has stabilized. When it stabilizes, we know the water has been lost. And by doing another mass by difference calculation, we can figure out the mass of water lost. Starting with the crystals hydrated minus the dry stuff, we know how much was water by mass. We put that mass over the mass of the original hydrated crystal times 100 and we'll get the percent hydration. To do that same calculation experimentally, you're going to need your periodic table and calculate your molar mass of the hydrated substance and then put on top the mass of water to figure out the percent hydration. And again, that's going to be utilizing the periodic table, not your experimental data.
So we've got a couple of experiments where we specifically need to be worried about our glove protocols. And those experiments are the solution concentration, the titration standardization, and the titration for the vinegar concentration. So when we talk about those experiments, it's absolutely necessary that we wear gloves for the entire experiments. For the other experiments, gloves are recommended. They're not necessarily necessary. It's never that we don't want you to wear them, but you don't have to wear them for the other experiments. For these, it's necessary. So I want to show you how to properly put on a pair of gloves, how to take them off, and then talk about what are proper protocols for using those gloves in those experiments. So let's talk about how we put those gloves on. So we're going to take gloves out of this container. Here's 1, here's 2. I'm going to set those down. We're going to make sure that we put them on appropriately. So we want to make sure that we get our thumbs into the thumb spots on our gloves. So that's 1. I want to get that over my watch because I want to make sure I don't kill my watch while I'm wearing it. And then I have my second one, if I can get this thing sorted out because they're all shoved in there and not necessarily easy to put on. Some people take their rings off before they do this. It depends on how big your rings are. I have ones that are tiny so I don't break through my gloves. That was a decision we made. But these are how I put them on. Putting them on is the easy part. Okay? Taking them off is not the easy part. When I'm in the lab and I'm working with these gloves, everything is fine. If I have to leave the lab for whatever reason, I need to go to the bathroom, I need to take a phone call, I need to eat something, I need to do something outside of the lab, including taking a drink, then I need to take these gloves off. So if I'm going to take these gloves off, I can take the first one off fairly easily, right? Fairly simple. But when I go to take the second one off, I want to hook my fingers inside of it, grab a hold of the inside, and then pull it off like that so that I'm holding the inside when I'm dealing with it, not the contaminated outside part of the glove. And then I take those off. I'm then going to wash my hands to make sure that I get anything off of my hands that shouldn't be there, because sometimes we accidentally get chemicals inside. Okay? And then I'm going to go do whatever I need to do. When I come back to the lab, I'm going to go to the front bench. I'm going to wash my hands again, just because I'm paranoid. And then I'm going to put on another pair of gloves. And I'll do that before I handle anything in the normal part of the lab. Okay, because chemicals can be just about anywhere. So we want to make sure that we're dealing with clean hands before we put them back into those gloves. Now, things that we need to make sure that we're dealing with when we talk about these experiments. We put those gloves on before we handle anything, because you may not be the first lab for that week. So the things that we're dealing with may not be as clean as we want them to be. So we want to make sure that we're dealing with, everything in gloves. So make sure we've got those dealt with the gloves on. Anything that we deal with in the lab needs to be done that way. Anytime anybody is working with anything, doesn't matter if it's chemical or not, for those labs, we need to be wearing those gloves, okay? So I think that's everything I need to talk about with the gloves. So thanks, guys. I appreciate it.
Okay, so I'm going to show you how to weigh a solid out, and then also how to do what we call heating to a constant weight. Heating to a constant weight. Both of these techniques are going to be used when you do the alum and the decomposition of baking soda labs. So to weigh out a solid, all right, here, balance on, there's your tare, put your weigh boat on, tare, okay, right there. Okay, now what you're going to do here is you're going to get a spatula or a scupula, and okay, these labs ask for 1 gram. Okay, so what I want to show here is you're adding. Okay, so you're adding and you're adding. Okay, and you're going to keep adding until obviously this says 1.00 gram. Okay, but let's say I'm adding, and then someone come up and for whatever reason, right? Oh no, look what happened. I am over 1 gram. This can't be happening. Do not put it back into the bottle. Okay, once you take this out, the solid out of the container is now contaminated. So the worst thing that you can possibly do is put it back in here. Do not do that. So what you're going to do is just get like another container and then take it out and bring it back to 1 gram. Bring it back to 1 gram. Just take it out, bring it back to 1 gram. Done. And then you will dispose of any excess according to the directions that are in your lab manual, okay? But do not put any extra back into the bottle. Done. Now you're going to record the weight as you see it. Now try to get close to 1.00 gram. Take your time as you can. Now, this is your solid, okay? This is the weighing of the solid. Now, what I wanted to show here also is that when you're going through both of these procedures, you're going to come to a point where you're going to have to be doing heating to a constant mass. Okay, so heating to a constant mass, what does that mean? All right, we use this technique for 2 different reasons. Okay, one reason, or why would you use this technique? You would use it to dry off a product, get all of the water off of a product, which is why you're doing it in the alum lab. And another reason why you would use this heat technique is to make sure that a reaction has gone to completion, which is why it's being used for the baking soda lab. Okay, so when you go to heat to a constant mass, okay, you're going to have your solid in the beaker. Okay, solids in the beaker. And we're using a hot plate. The key word here is hot. This surface is going to get very hot. We're setting it to get about 200 to 250 degrees Celsius. You do not want to have anything near the surface, including any pens or anything. They will melt. You don't want to touch this with your hand, okay? Now, when you go to turn it on, you see there's a heat and a stir knob. We're not stirring anything today. We're heating. All right, so you're going to turn this and look at the protocol, the experimental procedure to see exactly what setting you're going to start. For the alum and the baking soda lab, you're starting at 200 degrees. So you just adjust this to 200 degrees. Okay, 201. Okay, and now you're going to give it a moment. It's flashing. When it stops flashing, that means the temperature has reached that point. Okay, so it takes a little bit of time for it to reach that point. Okay, but let's just pretend like now it's hot. Yours is hot. You're going to take your beaker with your solid and you put it directly onto the hot plate. You're going to let it stay there for however long as is specified in the procedures, 10 or 15 minutes. And then you're going to remove the beaker off the hot plate. But what you have to do here, if you touch this beaker, you're going to burn your fingers. Don't do that. So you can use an oven mitt, which we have right here, or you can use beaker tongs, which are in the lab as well. Okay, but you do not want to use your hand unless you want to burn your hand. Don't do that. Take it off. And now don't put it directly on the bench top. You're going to put it on this wire gauze. Put it on there, let it cool, okay? Now pretend this is hot. Don't put it onto the balance and expect to get accurate results. When you put something hot onto the balance, it causes the air around it to flow upward, which is going to interfere with your reading, okay? So let it cool for 5 minutes, and then you're going to put it onto your scale and then to weigh. Like tare first, of course, and then weigh. Not adding any extra digits. And what is the units? Don't forget to put the grams. Done. Okay, so you're going to weigh this, you're going to record it. Now you're going to do this again. Okay, you're going to do this again. Put it back onto the hot plate for the specified time, which I believe is 5 minutes for the second cycle. After 5 minutes or the allotted time, you're going to do what? Now also note this, you need to crank up the temperature at this point, okay? And we're going to crank it up to 250. So crank up that temperature first. Let it adjust, okay, 250, 260. It doesn't have to be perfect for this part. Okay, then when this stops flashing, your temperature is ready to go. For the sake of time, I'm pretending we're there. Put it on there for 5 minutes, and now are you going to touch it? No, you're not. You're going to put it on your oven mitt, and now are you going to put it on the bench top? No, you're not. You're going to put it on the wire gauze. Put it on the wire gauze for 5 minutes. Let that thing cool. Let it cool. Now we can put it onto the balance. I'm going to tear this. I'm going to put this on here. There's my weights. Now, to make sure that we are ready to go, you need to do what? To make sure like we've gotten all the water off of this, or my chemical reaction has gone to completion. Okay, you're going to compare the two weights that you just took, all right, as shown on this slide. You're going to take the two weights and you're going to take the difference. If the difference is more than 0.01 gram, we cannot say that we have a completely dry alum product. We cannot say that the baking soda has been completely decomposed. So we are going to carry on and do it again. You're going to heat, you're going to cool, you're going to weigh. All right, and now take that number, that weight, from the weight of the second heating, okay? Because the bottom line is that you want 2 consecutive weights where the difference is less than 0.01, okay? So you're going to keep repeating this cycle until you achieve that, okay? And now I'm finished. Let's say, okay, oh look, I got the 0.01, I crossed that hurdle. What are you going to do? I'm done, I'm going to leave. No, you're not. You're going to do what? You're going to make sure that your balance is clean. Okay, brush it off for the next person. Clean your balance, okay? I'm not turning it off. Other people are using it. I am, though, going to turn off my hot plate. Turn it off because it's very hot. Not only am I going to turn it off, I'm also going to unplug it as well, okay? And then just remember, it's very hot. Don't touch it. No pens near it. Watch for your shirt, anything like that. Okay, thanks.
So we're going to be talking about data collection and potential errors, and we're going to be talking about this in general. It's going to apply to all of our labs, so this is going to be the same conversation you're going to hear for every lab, but I need you to pay attention to the same things and learn to apply them for each of the experiments. When we talk about data collection, there are certain pieces of data that you're going to be asked to collect. Depending on which lab it is, that's going to determine which pieces of data you're going to be asked to collect. It's not going to be the same every time. Sometimes we're going to ask you to collect one piece of data one time. And that's because we're interested in making one observation about that piece of data. Okay, so it's just one piece of information that we're going to collect that one time. That's typically a qualitative observation that we're looking to make, so just information without a lot of specifics about it. Okay. On the other hand, we may want to take that piece of data twice to see if it's reproducible. Okay, so typically if we're going to do that, it's going to be a numeric piece of data, and we're going to be very specific about how we take that piece of information. Now, we either take it once, twice, or many times. Now that many times is going to depend on exactly what we're doing and how we're doing it. In this class, we will limit that to 3. It never goes beyond the 3. But out in the real world, that many times could be 5, 10, 20, 50. Could be any of those things. The reason for that is because it becomes statistically significant. So if you've taken Math 120 and you know about statistics, you understand that we need multiple data points to be able to determine if those data points are statistically significant. So we need to know if that's really true for the data points that we've taken. We can't get rid of them if they look wonky if we don't know what wonky actually looks like. So we need to take multiple points to be able to see if that data is real or not. Okay. We typically don't do that in this class until we get into the later labs. So the titration labs, the first times that we start looking at that number of data points. We do start taking more data points as we go forward. So in the beginning, we take 1 data point. Later on, we take 2 data points. At the very end, we start taking 3. If you have the privilege of taking CHEM110, then you get to take many data points the whole time. So look forward to that. Okay. Those are important things for us to be paying attention to. The other thing that you need to be thinking about is what kind of data are you taking? Because the kind of data that you're taking determines how precise you need to be with the information that you're collecting. The instrument that you're using typically gives you an indication of what kind of precision you need for that particular measurement. When we talk about the electronic balance, there's only a certain number of numbers on that balance that we can look at. There's no way we can estimate beyond those numbers. So that's what we're going to record. But when we talk about something that's a volumetric piece of equipment, we can usually estimate beyond the last thing that we can look at. So on a graduated cylinder, we can estimate beyond the last measurement that's there, in between those last measurements that are there, and so we can estimate that last data point. When we talk about something like a volumetric pipette, which is one of these guys, for this, there's a finite measurement that's here, and we can't estimate beyond that. We know exactly what that is, and so if this is a 1 milliliter pipette, we know that this is 1.00 milliliters. That's the precision that we know for that particular instrument. So the type of instrument that we're dealing with will tell us what kind of precision we have for that number. It's important that you pay attention to that and record exactly what it is. You will see that when we're in ALEX, it will be very specific about that. So if you don't have the right number of numbers, that's going to be a problem. We need to know how many numbers it is because that determines our number of significant digits, which then determines how significant those calculations are going to be, which then determines how significant our answers are going to be. So this becomes something that we have to carry through all of the calculations that we do. That's important. Okay. So that's all of the data that we collect, how we have to be careful with the numbers that we're collecting, and the type of information that we're looking at. Now, every piece of data that I collect has to have a unit. If I see numbers that don't have units, most of us will flip out about that. Okay? Units have to be there. Is it a gram? Is it a milliliter? Is it a kilogram? Those are important. We have many times that scientific numbers are recorded in the US and then sent to the UK, and assumptions are made about what units those were, and then an assumption is made when they go to the UK, they do something with it, they make some kind of conversion about it because an assumption was made, and then they do some conversion to it before they send it back to the US, and then the US gets those numbers back, still without units, they do some other conversion to it, and then some $2 billion mistake happens. Welcome to the Hubble telescope. Okay? These things happen, and this is a really big deal. If you've made it one of those, been part of one of those calculations where a $2 billion mistake has happened, that's the kind of thing that gets you fired. So a simple putting the unit at the top of the column of numbers is a really big deal. So recording your units at the top of a column or with that number becomes very important. It's a habit you should be building now. So the numbers that you're recording should have those units. Okay? So make sure you're doing that with your lab materials. Make sure that you're doing that on your tests. If they're not on your tests, that's a problem too. Okay? So those are the data that we're collecting, the number of significant figures that we have to have, the type of data that we're collecting, i.e. the units that they are. And then we need to talk about potential errors. everything that I measure has a potential error that can go with it. So if I'm using one of these volumetric pipettes and I'm not particularly skilled at doing so, there are errors in the way that I may be doing that. It may be too high, it may be too low. There are inherent errors in that particular measurement. If I'm particularly precise in how I do it, then I don't have to worry about those errors. But if I'm not precise, I need to be honest about that. Okay? That's something that I need to record when I'm doing my data collection. So if I say to myself, okay, I wasn't paying that much attention and it might have slipped down below where it should have been, I need to write that down because that's a potential error. That can affect a lot of the things that happen after that. Because if my volume was too small, then the concentration that I'm going to end up with is going to be too high because my mass is going to be in a smaller volume, which means a larger concentration, which therefore is going to affect all of the information that I'm collecting off of that concentration. These are implications that I have to be able to think about. Okay? So anything that you do may have implications down the road. So you have to think about what you did. If you took a mass on the balance, we always talk about it doesn't need to be exact. It absolutely does not. You do not need to spend a ton of time getting the exact number that we've asked you to get. Don't. It's a waste of time. But you need to record exactly what it was. Okay? And if you do what some students do, and you don't bring your paperwork with you and write down that number when you're at the balance, and you walk away and then record the wrong number, then that's a problem, because you don't know if it's too high or too low. So one of the things that you need to be aware of is that when you go to that balance, you should be taking your paperwork with you to record that number at the balance. One of the things that I do to my students is if I see them walking to the balance without that piece of paperwork, is I will follow them from the balance back to their bench, and I will sing things like 8675309 so that they forget whatever the number is. Or if I see them writing it on a small piece of paper, then I will take that paper and burn it, because that's who I am. These are things that you really should not be doing. They're bad habits that you cannot afford. Okay? Violations like that in terms of federal regulations are $10,000 per incident per day violations. That's expensive. Okay? Your company doesn't want that. And if you're responsible for it, that's something you can get fired for. Okay? So, those are important things to think about. All of these errors have places where they can cause problems. We want you to think about the errors that you may have. When we ask you about errors, an answer that is completely unacceptable is human error. What the heck does that mean? What errors did you make? What could you have done? I may have made mistakes in measuring. Okay, what measurements could I have made mistakes with? Was I imprecisely reading my volumes because I was too lazy to pick up my things so that I was reading the meniscus correctly? If that's the case, then maybe we should talk about making sure that we're having that meniscus at eye level so that we're seeing it appropriately. Okay? Are there things that we could do differently? Now, just because you're not aware of that at the beginning doesn't mean you can't improve on it as you go forward. That's part of the reason that we look at this after we do an experiment, because we're learning to look at how we did that experiment critically to see how we could do it better the next time. We need to be able to do that for ourselves and for the next person who does this lab, so that we can say, hey, try this instead, do this differently, so that maybe you can do it better next time. That's an important part of our ability to be scientists, is to be critical about what we did. It doesn't mean you're wrong, it doesn't mean you do it badly, it just means that you have to be honest about what was done. Okay? So be willing to look at what you did and what are real places that you could have made a mistake. Okay? Those are important things. When we transfer solids, often we lose some of that material. So make sure that you've noted it places where that may have happened, especially if you actually see it during the experiment. You should write that down. You should talk about the fact that that happened. So any of those errors should be noted in your paperwork, and it should be something that you talk about in the paperwork for your experiment. Okay? So those are the potential errors that you may see. Now, those are all going to be based on the particular experiment that you're doing. I'm not going to specify for each lab where those things may be because it's your job to figure out where they might exist. Okay? This is a gentle reminder that you need to be looking at every experiment to see what kinds of things was I recording, what kind of mistakes could I have made, what things do I need to be paying attention to. So that's my spiel about data collection, units, errors that you might have made, and how those errors could implicate the data that you're looking at. So hopefully that will help you with some of those things and get you on the right track. Thanks, guys.